some more stereochemistry problems in this video. So, which of these molecules are mesoisomers? Okay, so which of these molecules are mesostructure? Okay, so this one, so they're asking if there is more than, if there is a mesostructure, and also if there is more than one. Okay, so this one is not a mesostructure. It doesn't even have a chirality center. As you know, mesostructure is something that has a chirality center, but because of the mirror symmetry in the molecule, the molecule is rendered optically inactive. Okay, all right. So if you look at the second structure, first one does not even have a chirality center, so it's just an achiral molecule. The second one, if you draw it from this, looking at it from this angle, right, it's going to look like this. Okay, and then those are the bonds. Sorry, it's not touching, but yeah. So you have hydrogens here, chlorines here, and there is a mirror plane in this molecule. And this is a chirality center: hydrogen, carbon with chlorine, chlorine, and a carbon with no chlorines. And this is also a chirality center, but there is a mirror symmetry that will render this whole molecule optically inactive. That's what meso is. So 2 is a mesostructure, and 3 is not a mesostructure. So that's a hydrogen here, and there's a chlorine here. Okay, hydrogen and chlorine. Therefore, this is not a mesostructure. This molecule and its mirror image are going to be enantiomers, whereas this one is not going to have a mirror image that is non-superimposable. So option 2 is the only one that is a mesostructure. So we have to identify what the correct stereochemical description of these two Fisher projections are for this problem. So we have to literally write down the Fisher projection, and we have to assign the absolute configurations on the chirality centers. So let's look at the first structure on the left here. So we have CH2OH, and then here you have OH and hydrogen, OH and a hydrogen here, and a hydroxy and a hydrogen, and here you have a aldehyde group. Okay, so let's call this carbon atom A. Let's label the carbon atoms. So this is A, B, C, D, and E. So we have to find what the configurations are for B, C, and D. So now let us provide assign priority. So this is highest priority for carbon D. So that's number 1. Between the other groups, this is obviously priority 4. And between E and C, C is going to be higher priority because you have carbon with oxygen, carbon with an oxygen, but there are 2 hydrogens, whereas here there is 1 hydrogen and this large group. So therefore this is priority 2. That makes this priority 3. So 1, 2, and 3 counterclockwise, but 4th priority group is horizontal. Therefore this is an R center. This is an R center over here. Okay, so now let us look at the second carbon. Okay, so now for second carbon, priority 1 here, and then for the carbon atom on the top and the bottom, here you have carbon, that's a tie, carbon with an oxygen, carbon with 2 oxygens. Therefore this is going to be second priority, and then this is going to be third priority, and hydrogen here. Therefore 1, 2, and 3 clockwise, but since hydrogen on the fourth on the horizontal position, this is going to be an S center. Okay, so now for carbon B, number 1, number 2, because you have carbon with 2 oxygens here, and this is number 3. This carbon is number 3. So 1, 2, and 3 counterclockwise, 4th priority in horizontal. So therefore this is an R. Okay, so this is an RSR molecule. So this is for B carbon it is R, C it is S, and D it is R. Now for this, let's draw the same thing here. OH here, hydrogen, and OH and a hydrogen and a CH2OH. Okay, so this is carbon D, same as what we have here. So 1, 2 as we previously saw, so this is 1, this is 2, this is 3 clockwise, but hydrogen on the 4th position, therefore this is an S center. 1, 2, 3 counterclockwise, hydrogen on the horizontal, therefore this is an R center. 1, 2, 3 clockwise, hydrogen in the horizontal, this is an, so 1, 2, 3, this is an S center. S, R, S, R, S, R. So if you look at A, B, B, C and D, B here is an R, C is an S, D is an R. B is that is an S, that is C, which is an R, and this is carbon atom D, which is an S. So RSR, SRS, therefore they are enantiomers. Okay, so which diastereomer is most stable? Okay, so in between these 4 structures, they're all diastereomers of each other. They all have the same carbon centers that are chirality centers, but the groups are switched from each other, therefore they are diastereomers of each other. So here we have a methyl group in the equatorial position, ethyl in the equatorial position, hydroxy in the axial position. So this is going to have a certain stability. Methyl in equatorial, hydroxy in equatorial, ethyl in equatorial, or isopropyl, sorry, not ethyl, isopropyl in equatorial. So all big groups are in equatorial, so this is going to be very stable. Methyl goes to axial, the other 2 are equatorial, these 2 are axial, this is equatorial, therefore so here you have this in axial as well. So whereas here all big groups are in equatorial position, therefore that makes this the most stable diastereomer. Okay, so which reaction would yield a meso product? Okay, so this one is going to give, so option A is going to give you that this carbon is attached to only 3 different groups. These 2 are the same, this is the same, therefore there is no chirality center here, and therefore this is not going to be a meso product. If you look at option B, this is A, B is going to give you bromine, but the bromines are going to be on the opposite sides. So bromine here, hydrogen here, bromine here, hydrogen there. That does not have a mirror plane. Therefore B is going to be not a meso structure. It is an optically active compound. So if you look at C, just like A, C is going to give you something that does not have a chirality center. So D, if you look at it, D is going to have, so let's look at it from this angle. Okay, so the hydrogens are going to be on the same side, which are hydrogens that are already there, and the deuteriums you're adding are going to be on the same side as well. So now this has a mirror plane, therefore D is going to be the right option. So what is the relationship between these two structures? Right? So let's draw them. Hydrogen there. So you have a hydrogen here and an OH here, right? So this is 1,2 dihydroxy, this is 1,2,3 dihydroxy. They have different connectivities altogether. They don't have the same connectivity but different orientations. They have a completely different connectivity, and therefore they are going to be constitutional isomers. Okay, they are not identical molecule, they are not stereoisomers. Stereoisomers are going to be something that will have the same connectivities, like for example what I'm drawing here. So let's say you have the hydrogen and the hydroxyl in the same position on the first one, but if you switch the hydrogen and the OH on the second one, right, now these two are going to be stereoisomers, they are going to be diastereomers. If you take this molecule and its mirror image, they are going to be enantiomers, right? Whereas here the connectivities are completely different, and therefore they are going to be constitutional isomers. They are not going to be stereoisomers. These two are stereoisomers, this and its mirror image, this and its mirror image, they are going to be stereoisomers. whereas this and this, they are just constitutional isomers. In fact, to be more precise, they are positional or regio, they are the same. Regio isomers or positional isomers. Okay. Alright, so which Newman projection corresponds to point A, which is that's the point A, on the graph of the potential energy versus rotation of the CC bond. So if you look at this, this is a staggered conformation. That's an eclipse conformation. That's the highest energy eclipse conformation. This is lower energy eclipse conformation. And that's point A, which is going to be a staggered conformation, which is higher in energy than the staggered conformation you see at 0 degrees. Okay. So we are looking at a staggered conformation. These two are eclipsed, therefore you can ignore them right away off the bat. Between C and D, you can see that the higher bulky group, they are farther away from each other. Here this is also staggered conformation, but this is something that is closer to each other. Therefore D is going to be point A, whereas C is going to be that. Okay, in fact we can do this. This is going to be the eclipse conformation, which is going to have the highest energy, and this is going to be the eclipse conformation, which is going to be lower energy. Okay. All right. Which of these molecules could have an enantiomer? So this one, because there is a mirror plane, this is a mesostructure. This cannot have an enantiomer. This one, it's going to be two chirality centers, and this is not a mesostructure, right? This is not a mesostructure, therefore this mirror image is going to have a chirality, is going to have enantiomers. There is no chirality center in this at all, therefore you cannot have enantiomers here. And again, no chirality center, both groups are the same, and therefore these are not going to have enantiomers either. And these two are related to each other as cis trans molecules. They are like geometric isomers. They are diastereomers, but they don't belong to each other as, or they are not related to each other as enantiomer, as like they are not going to have enantiomers, whereas this is the only one that is going to have enantiomers.